So now towards the very end of this lecture series, I will give you the promised application to celestial mechanics on the inversion of the Kepler equation. Let me begin this lecture with a beautiful epigram in Ptolemy's Almagest. I know that I am mortal by nature and ephemeral, but when I trace at my pleasure the windings to and fro of the heavenly bodies, I no longer touch the earth with my feet. I stand in the presence of Zeus himself and take my fill of ambrosia. This book of Ptolemy, the Almagest, appeared in AD 145, which is very old as we can see. Now, the Almagest of Ptolemy was one of the most influential books on astronomy, and it remained one of the most authoritative accounts for nearly 13 centuries until Copernicus's book De Revolutionibus appeared. Ptolemy's mathematics is very complex. He believed in the geocentric universe, placing the earth at the center of the universe, and to accommodate the retrograde motions of the outer planets, he had to introduce epicycles and 30 nested epicycles. The history is very interesting of Ptolemy's Almagest, and one should mention that no other book except the Bible had such an everlasting influence and unchallenged for such a long period of time. So this is Ptolemy. In fact, Gauss had studied Ptolemy very carefully. So now let us look at this last chapter of this course, or rather the penultimate chapter, because this will be followed by a chapter called Odds and Ends. And we discussed the original problem that led Bessel in 1824 to introduce the functions that bear his name. Wilhelm Bessel was an astronomer at Königsberg, and his chief interest was the study of the orbits of comets. We must begin by recalling the three basic laws of planetary motion enunciated by Johannes Kepler. The discovery of these laws forms an interesting culmination of classical astronomy. You see, equipped with his calculus, Isaac Newton, with his laws of dynamics, was able to explain the motion of the planets, the precession of the equinoxes, and the formation of tides. Astronomy, hitherto an empirical science, transformed into a dynamical science. The first two laws of Kepler were enunciated in 1609 in his De Motibus Stellae Martis. Kepler's first law says that the planets move around the sun in elliptical orbits with the sun at one focus. Kepler's second law states that the radius vector joining the sun and the planet sweeps out equal areas in equal intervals of time. This statement is just a reformulation of the conservation of angular momentum. The third law, which is an approximate law, neglecting the masses of the planet, appeared much later, almost a decade later, in Harmonices Mundi. Kepler's third law says that the square of the period t is proportional to the cube of the semi-major axis of the orbit. The constants of proportionality was determined by Gauss in his famous book on astronomy, Theoria Motus Corporum Celestium, and is today known as the Gaussian gravitational constant. So these are the three laws of Kepler. So let us now see what is the inversion problem of Kepler. Now, before I introduce the Kepler equation and the inversion, I must explain to you why this is important. After all, the problem of solving the two-body problem, of integrating the equations of the two bodies, is basically a system of differential equation. Where does this inversion of the Kepler equation come in to play? So let us set the problem against the general backdrop of the theory of nonlinear ordinary differential equations. So let us consider a system of ordinary nonlinear differential equations in Rn. Equation 8.1 that you see in the slide, dyj upon dt equal to fj of y1, y2, yn, j running from 1 to n. In other words, 8.1 is an autonomous system of ordinary differential equations. The time variable t doesn't explicitly appear on the right hand side in the functions fj. And we are going to assume that the fj's are smooth functions. And so there is no problem in appealing to the fundamental existence uniqueness theorem of ordinary differential equations. So what does it mean to say that we want to solve 8.1? It means that we will be given some initial conditions, say y1 of 0, y2 of 0, yn of 0. So for this set of initial conditions, there must be a unique solution, and we want to find that unique solution. The solution, after all, is a function of t. So y1, y2, yns are functions of t. Put these functions together and form a vector in Rn. We get a map t mapping to y1t, y2t, ... ynt. In other words, this is a curve in Rn. So solving the system of differential equations 8.1 means we are trying to locate a very specific curve in Rn with a very specific parameterization. To illustrate this idea, let us look at a very simple example, equation 8.2 that you see in the slide, which is the equation of a harmonic oscillator, a simple harmonic oscillator, x dot equal to y and y dot equal to minus x. Of course, you multiply the first equation by x and second equation by y and add up. What do you get? X dot plus y dot equal to 0. But what is x dot? X dot is the derivative of x squared by 2. Y dot is the derivative of y squared by 2. So we are seeing that ddt of x squared plus y squared is 0, which means x squared plus y squared is a constant. Let us record this observation. So we get that x squared plus y squared equal to constant. And what is the value of this constant? You plug in initial conditions. X of 0 is given to you, y of 0 is given to you. Put this into this equation and you get the value of the constant. In other words, what we have is that if you take a solution of the system of differential equations 8.2, that solution is a pair of functions x of t and y of t. This pair of functions x of t and y of t satisfies this equation, x of t the whole squared plus y of t the whole squared equal to constant, and the constant can be determined by initial conditions. So the function x squared plus y squared obtained here is called a first integral. Let us define it in general terms. A non-constant smooth function phi of y1, y2, yn is said to be a first integral for the system of differential equations 8.1 if phi is constant along solutions. That is, phi of y1t, y2t, ynt is constant along every solution y1t, y2t, ynt or the system of ODEs. Equivalently, differentiate 8.3. 8.3 is a constant. Differentiate it, you're going to get 0. But how do you differentiate a composite function? Grad phi dot with derivative of y1, derivative of y2, ... derivative of yn. But what is derivative of yn, derivative of y2, derivative of yn put together? f1, f2, fn. That is grad phi dot f equal to 0. That's the equivalent condition for phi to be a first integral. So in other words, x squared plus y squared is a first integral. So it is constant. This function x squared plus y squared is constant along every solution of the differential equation. So what we see is that if we have a first integral, what does it mean? It means that phi of y1, y2, yn is constant, and that means that the solution that we are looking for, the solution curve t going to y1t, y2t, ... ynt, that solution curve that we are looking for, instead of looking for it in Rn, we simply have to look for it in this locus 8.4. Equation 8.4 represents an n-1 dimensional hypersurface in Rn. So for example, for the harmonic oscillator, we exactly know what it is. The solution xt, yt is on a circle, x squared plus y squared equal to constant. So geometrically, we have determined the curve. We have determined the solution curve as a curve, but what we are not determined is the exact parameterization. We'll come back to this presently, but before that, in the general setup, what have we gained? We have gained the fact that instead of locating the solution y1t, y2t, ynt in Rn, we are reduced the problem to locating it along the hypersurface 8.4. This equation 8.4 is an n-1 dimensional object, and Rn is an n-dimensional object. In other words, we have reduced the problem from an n-dimensional problem to an n-1 dimensional problem. There has been a dimension reduction in our solution process. For example, suppose if phi of y1, y2, y3 happens to be y1 squared plus y2 squared minus y3 squared. The constant happens to be 1. Then what is that equation 8.4? The equation 8.4 is y1 squared plus y2 squared minus y3 squared equal to 1. It's a hyperboloid of one sheet. It's a two-dimensional surface in R3. And so the solution that we are looking for is along some two-dimensional surface. Namely, instead of a three-dimensional problem, we are now reduced the issue to a two-dimensional problem. Now, when we looked at the harmonic oscillator, we were already in a two-dimensional problem. X dot equal to y, y dot equal to minus x. Now we got a first integral x squared plus y squared equal to constant. So we already reduced it to a one-dimensional problem, but the curve itself is one-dimensional. So effectively we have found the curve, except that the curve has infinitely many different parameters. The circle x squared plus y squared equal to c is the curve that we are looking for. But what we don't know is the parameterization. The circle has infinitely many parameterization. For example, it has parameterization cosine t, sine t, cosine 2t, sine 2t, sine 2t, cosine 2t, sine 2t minus cosine 2t, 1 minus t squared by 1 plus t squared, 2t by 1 plus t squared. The circle has infinitely many parameterization. But our solution to the differential equation is a very specific pair xt and yt. So which one of these infinitely many parameterizations of the circle is the actual solution? That's the problem that we are trying to find out now. So now we know that x squared plus y squared is c. So we can always put x equal to cosine of f of t, y equal to sine of f of t. I have taken the constant to be 1 for simplicity, and the capital F is a function that needs to be determined. So let us substitute x equal to cos ft into our differential equation 8.2. We must substitute x equal to cosine of ft, y equal to sine of ft into this differential equation 8.2. What do we get? We get f dot equal to minus 1. Immediately that gives you f of t equal to alpha minus t. And so we have immediately found x equal to cosine of t minus alpha, y equal to minus sine of t minus alpha as expected. These are the solutions of the harmonic oscillator. Now the harmonic oscillator was a very simple example of a differential equation, and the procedure turned out to be quite easy. Now let us go to a slightly more difficult example, a more sophisticated example, the example of Euler's equations for a spinning top. This is a system of 3 differential equations in R3. So what are the differential equations? Ax dot equal to b minus c yz, by dot equal to c minus axz, cz dot equal to a minus b xy, equation 8.5 that you see displayed in the slide. A, b, c are positive constants, and we may assume that a is bigger than b and b is bigger than c just for definiteness. And the a, b, c are the principal moments of inertia or the spinning top. But we are not concerned with the physics of the problem. You can pick up any book on physics and you can see how 8.5 arises, but we are interested in the underlying mathematics. So now multiply the first equation by x, second by y, third by z and add up. What do you get? Ax x dot plus by dot plus cz z dot equal to 0. Again, xx dot is derivative of x squared by 2, y dot is the derivative of y squared by 2, z dot is the derivative of z squared by 2. And we see that the derivative of ax squared plus by squared plus cz squared is 0. So ax squared plus by squared plus cz squared is constant along solutions. In other words, it's a first integral. Now let's do something slightly different. multiply the first equation in 8.5 by ax, second by by, and the third by cz, and then add up. The same rigmarole will now give you that a squared x squared plus b squared y squared plus c squared z squared is constant. So now we got two first integrals, 8.6. So we must set them equal to constant. They are constant along solutions, but our solutions come up equipped with initial conditions. So plugging in the initial conditions, we can fix the value of the constants. Let the value of the constants be alpha and beta. We get what? Our solution curve lies on the pair of ellipsoids ax squared plus by squared plus cz squared equal to alpha, a squared x squared plus b squared y squared plus c squared z squared equal to beta. These are the surfaces and they are ellipsoids. These two ellipsoids are going to intersect along a curve, and that is the curve that we want, except we do not know the parametrization. So apart from the parametrization, the curve as a geometrical object has been nailed down as the intersection of these two ellipsoids given by 8.7. Now, which one of the infinitely many parameterization qualifies to be a solution of the ODE? Any curve has infinitely many parameterizations, and only one of them is going to be a solution of our ordinary differential equation. Our problem is to nail down the correct parameterization. So let us proceed to find out. So let us write x squared plus y squared plus z squared equal to u. You see, we already have two equations 8.7, and by looking at these two equations, by symmetry, cook up one more equation, x squared plus y squared plus z squared. But x squared plus y squared plus z squared is not a constant, it's a function of time. Let us call that u. So u is a function of time. That's equation 8.8. Now we must solve 8.8 and 8.7 simultaneously for x squared, y squared, z squared, and we get our three functions x, y, and z. Say x is a function of u, f of u, y is a function of u, g of u, z is a function of u, h of u. 8.9. I leave it as an exercise for you to determine f, g, and h explicitly. That is not very interesting, but they can be computed by solving three equations simultaneously. Okay, if x is f of u, what is x dot? X dot is f prime u into du by dt. But what is x dot? B minus c upon a yz. So f prime u into du by dt equals b minus c upon a into yz, but the yz is gu and hu. So that's exactly the equation that you have, and what you have found is a scalar first order ODE. So you divide by f prime of u, and the equation for u takes the following avatar: du by dt equal to psi of u, or u dot equal to psi of u, where psi is a scalar function of u. It's a simple example of a variable separable equation, and we are very happy because we can immediately integrate it. But our happiness is going to be pretty short-lived, because when you integrate the variable separable equation, what do we get? We get equation 8.10. T becomes a function of u. T becomes integral u of 0 to u ds by psi of s. There are two issues. One of them is a minor issue and the other one is a major issue. The minor issue is the fact that you may not be able to compute this integral in closed form, but that's really a minor issue. Even if you are able to compute this integral in closed form, there is still one more problem left. We got t as a function of u. What we want is u as a function of t. We have to invert 8.10, because only when we find u as a function of t, we can substitute in 8.9 and get x, y, z as functions of t. It's only when we do this that we can definitely say that we have solved the system of differential equations. So solving the system of differential equations really means expressing u as a function of t. What we have done is express t as a function of u. There's an inversion problem. It is exactly this inversion problem that is going to lead us to the Kepler equation, and solving this inversion problem is going to lead us to Fourier analysis, and the connection with Fourier analysis is thus apparent. Okay, now what happens is that generally if you have a system of n differential equations 8.1 and you have a system of n minus 1 first integrals, which some additional conditions displayed in the slide, then what happens is that these first integrals, they describe for you n minus 1 hypersurfaces which intersect along a curve, and this curve of intersection is the curve that we are trying to look for, and that's the curve that we want, except for parametrization. Finding the correct parametrization involves one integration like 8.1 and one inversion. So the next problem is, how do we get the first integrals? Who is going to give us the first integrals? So for the Euler's equations for a spinning top, we got two first integrals, 8.6. How could we guess that these are the two first integrals? For the harmonic oscillator, we had a first integral x squared plus y squared. How could we guess that there was an integral like that? Answer is very simple. For the harmonic oscillator, x squared plus y squared is the total energy of the system, and the total energy is conserved, and so the constancy of x squared plus y squared is basically the law of conservation of energy. What about the spinning top? Ax squared plus by squared plus cz squared. A, B, C are the principal moments of inertia, and x, y, z are the components of the instantaneous angular velocity. So what we see here is the rotational kinetic energy of the spinning top, and we're ignoring the effect of gravity, so there is no torque, and so the rotational kinetic energy is conserved. That is why ax squared plus by squared plus cz squared is conserved. What about a squared x squared plus b squared y squared plus c squared z squared? It is the magnitude of the angular momentum. The angular momentum is going to be conserved, the magnitude, and so that is 8.6. So physics usually gives us first integrals, a supply of them, such as the law of conservation of energy, for example. The other source of first integrals is geometry. Geometry may sometimes provide us with first integrals. When a system of ODEs exhibits a continuous one parameter family of symmetries, then there are associated first integrals. This is actually a theorem due to Emmy Noether. Remember that in the elementary courses, when you had a homogeneous differential equation m dx plus n dy equal to 0, what does homogeneity mean? The differential equation remains invariant under scaling transformation. When you replace x by lambda x, y by lambda y, the differential equation doesn't change. And this is a scaling symmetry, and lambda is a continuous parameter, and so there's a continuous one parameter family of symmetries, and by Noether's theorem there must be a first integral. Already it's a scalar first order equation, so one first integral means there is nothing more to do. You integrate it directly and you get the answer. That's why the method works. So geometry provides a supply of first integrals. So these are the two main sources of first integrals. So now let us come to the two-body problem that we are looking at. What is the two-body problem? It's a system consisting of two bodies, namely the Sun and the planet. In R3, the Sun and the planet is revolving around the Sun in R3. It turns out that neither is revolving around the other, both of them are revolving around a common center of mass. So the system is governed by Newton's laws of motion, which is a system of 6 second order ODEs for the instantaneous positions of the Sun and the planet. Equivalently, we are looking at a system of 12 first order ODE. A second order ODE can be written as a first order system. So we have 6 second order ODEs or 12 first order ODEs. So what are the variables? There are two bodies, Sun and the planet, 3 coordinates of position for the Sun, 3 coordinates of position for the planet, 3 coordinates of velocity for the Sun and 3 coordinates of velocity for the planet, totaling 12. So now we know that there are no external forces. So linear momentum is conserved, total linear momentum is conserved. So m1 v1 plus m2 v2 is going to be constant. So divide by m1 plus m2, since mass is conserved, we get that m1 v1 plus m2 v2 upon m1 plus m2, which is c, boldface c. That gives you three constants of motion, three first integrals. Now what is v1? v1 is x1 dot and v2 is x2 dot, where x1 and x2 are the positions. So we get ddt of m1 x1 plus m2 x2 upon m1 plus m2, that is c. So we can immediately integrate this and we get that m1 x1 plus m2 x2 upon m1 plus m2 is ct plus d. This gives us three more integrals. This says that the center of mass moves along a straight line. We'll continue this in the next lecture.